Welcome back to Lecture 2. Let's get started with electrical signaling. Now, we're going to kick off this lecture by talking about action potentials. Okay, so action potentials have this principle called the all or none principle. And what that means is if the threshold is reached, all the action potentials are the same size. So let's review. Now, when we say threshold, this means the voltage needed to open sodium voltage gated channels at the axon hillock. Okay, that kicks everything off. Now all the action potentials are the same size, so I want to show you folks this picture. Right now, what you folks are seeing, again, -70, you folks know that this is the area of the axon. It's at resting potential. But look at the amplitudes, right? So an amplitude is when you have a wave, how tall is that wave? That's what amplitude means, okay? Now, the amplitudes are all the same. Bang, bang, bang. Why? Why same amplitude? I'm so glad you asked. Thank you. Now, it goes back to your foundations, people. In order to ask the question, answer, in order to answer the question, why the same amplitude, you gotta go back to your foundations. You need to ask yourself, how do I get depolarization? That is where the answer is, okay? So press pause and ask yourself, how do I get depolarization? And that will give you the answer to the same amplitude. Press pause, come back, and now you're back. Now, this is how. Remember, in order to depolarize, I need to have two things. Number one, I need to have a gradient. Yes? So I need to have a sodium concentration gradient. This is my own shorthand, conc grad. It means concentration gradient. Okay? It's because the amount of sodium rushing into the cell to cause the cell, in this case, we're talking about action potential. So to cause the axon to become more positive, aka depolarization, is dependent on sodium coming into the cell, and we need to have a concentration gradient for that. Okay. Number two, what is sodium? A small polar ion. So here it depends on then how many sodium voltage gated channels are present and how many are open. Okay, because how many are open as well as how many are present is going to dictate how much sodium can come in based on the sodium concentration gradient. That is why all of the action potentials are the same size. And there's an all or none principle, is because just as long as I reach threshold and start to kick off sodium coming in through that axon hillock, all that sodium is going to start traveling down the axon and then kicking off all of the sodium voltage gated channels in the axon itself. Okay, now let's visit another principle. All right, now I just told you that amplitudes are going to be the same. However, the frequency of action potentials will differ. So let me show you folks another picture. And what you folks are seeing is the following. Action potentials are always going to be that same amplitude, aka same height, is because I have a specific concentration gradient, and I have a number of sodium voltage gated channels. Okay. Now, look at the frequency. Frequency is defined by how many times you have something in a given range of time. Okay, so here, what you folks are seeing on the left is amplitudes of action potentials, but which one is more frequent? The one on the left or the one on the right? The one on the right. You see how I have more action potentials in a given amount of time? That means a higher frequency signal. Okay, so let's just write that down. This area here, this is higher frequency. and this is lower frequency. Okay, same amplitude, but differences in frequency. Which one do you think is the stronger signal? Lower frequency or higher frequency? It is the higher frequency. Now, why different frequency? Thank you for asking. Now, the differences in frequency depends on the signal received. And this signal is being received from the previous or the presynaptic neuron, okay? I'll just put previous for right now. Previous neuron, okay? Because if I have a neuron, so it's this neuron number 1, and it keeps sending a signal. Let me draw that out because, we're visual people. Here's neuron number 1, and then this is neuron number 2. Oh, hello, 2. All right, now, if neuron number 1 keeps sending a signal and neurotransmitters keep binding to this neuron number 2 is going to keep having action potentials if that signal is strong enough. That's what you're seeing with the higher frequency, okay? So if I receive a lot of strong signaling, I'm going to have a higher frequency of action potentials, because those action potentials are going to keep lighting off, is because I keep opening up those sodium voltage gated channels in the axon hillock, okay? So it depends on the signal received, and what we mean is how strong a signal is being sent from the previous neuron. That's how we get a difference of frequency. Are you confused? That's okay, because we're still going to need to talk about neurotransmitters. So this is just for you to chew on, okay? Just chew on this, and we're going to talk about the mechanisms that govern all of this frequency stuff shortly. But what I do want to add, right, is that frequency is the code. Frequency is the code. This word code, because we're talking about the brain. The code that the nervous system uses to determine strength. To determine strength of signaling. Okay? All right, let's talk about this code. What's this code you speak of? So let me now talk about what's going on in the axon in order for us to get these type of action potentials with the same amplitude. All right, so what I'm showing you folks here is one neuron. Here's the cell body, and then here is the axon, and this is a myelinated axon, so this is a very long neuron. And then this picture up here is a blow up of this area, okay? So I have myelin, and let me just label it so we're not forgetting, okay? So this is my myelin sheath wrapped around the axon, okay? And then look, what do we have here? Nodes of RON-VA, okay? And so remember, I'm going to write it down in this area, and I don't want to confuse you. It's just more of because I need the space to write. So right in here, that is your node of RON-VA. Okay, now remember, if I want communication to travel down a very, very long axon, I have to have myelin so that I can keep that charge inside of the axon to help propagate the signal forward, okay? So in this direction here, this is traveling towards the axon terminal. And then up here on the left, this is where the cell body is, okay? All right, you folks with me? Good. If not, make pretend. Now, here we go. This is a node of RON-VA. You folks can see, right, is that I have only 4 sodium channels, sodium voltage gated channels. Therefore, I can only let so much sodium in, okay? And that tells you or shows you the mechanism behind how the action potentials are all the same height, aka same amplitude. Okay. Now what's not drawn here is that in this area, we're always going to have a sodium ATPase, right? Sodium potassium ATPase that's going to constantly now maintain that sodium gradient, right? So once the trigger zone, aka the axon hillock, propagates the signal down the axon, which is sodium rushing into the cell, all of these voltage gated channels are going to now have a more positive charge in here. They will open, cause sodium to come rushing in, and then causing this part of the axon to become more positive because sodium is traveling down its concentration gradient. Okay. And then what's going to happen here in this part of the axon is that these sodium voltage gated channels are going to become, the area in here is more positive. So they're going to open because that's what voltage channels do. They open at the appropriate threshold. So they will open and then sodium will come rushing in into this area. Okay. Now what's going to happen is the whole time the ATPase is going to be pumping sodium back out so it can maintain or correct that concentration gradient so we can start all over again. Now, once the action potential occurs and starts traveling down the axon, remember, we have to finish the action potential. So I'm going to draw one action potential just at this node of RON-VA. So remember, the action potential is going to go up. That's what you folks are seeing up in here, right? It's sodium rushing in. But remember, this is only half the story. What happens after sodium comes rushing in? Potassium leaves, right? And then when you have potassium leaving, that positive charge is leaving the cell, you're going to become negative. But remember, the potassium gates are slow to close. So I get this hyperpolarization area here, which means that in this area, the voltage gets very, very negative. So negative that these sodium voltage gated channels cannot open. They cannot open, even if they're reset. And that allows us now the mechanism to keep propagating the signal down the axon, down towards the axon terminal, and never backwards towards the cell body. Okay. Now, look at what's going on down here at the big picture. This is our neuron. So you can see then this type of signaling that's going from the axon hillock and literally then just jumping from node to node. This is something called saltatory conduction. And all that means, saltatory means jumping, because it looks like the signal is jumping is because it goes from node to node to node and nothing's happening in the myelin sheath. Here's a diagram showing you folks saltatory conduction. And all that means now is I'm propagating the signal or starting depolarization at the nodes of RON-VA. And that's why they call it saltatory, because it looks like the signal's jumping. It's not really jumping. It's just coming in through the node and traveling very, very fast because of the myelin, and then having the signal depolarize again at another node. So myelin allows you to have a faster signal. Okay, if you want a fast signal, you have to have myelin. And this is how myelin allows you to have fast signals. And the first thing is that it allows you now to reduce current leak. Now remember, in order for me to have a signal, it starts with depolarization. But in order for me to have depolarization, I have to have a concentration gradient for sodium. Yes? Okay, the same foundations, people, over and over and over. Now, everywhere in cells, in all membranes, in all plasma membranes of a cell, you're going to have leak channels, okay? And if you have a leak channel, then what's going to happen is your charge, electric charge, is going to start to travel laterally. And if you have a lateral movement of that charge, then you're going to lose conductivity. So if you wrap up the axon with myelin. Remember, this is a protein and fat. Do you think sodium or potassium is traveling in this area, in and out of this axon? Oh no, it's not, because it cannot permeate myelin. It is too thick. It is too fatty. There ain't nothing going on in this area in regards to ions coming in and out of the axon. The only thing that's going on in an area that's myelinated is you have ions traveling down their concentration gradient. Nothing is leaking. The concentration gradient can maintain itself. Therefore, you have sodium traveling very, very fast. Okay? Now, the second thing that allows myelinated axons to propagate a signal faster is because you don't have to pump so much sodium and potassium out of the node to get back to rest. Because remember, in order for you to have another action potential, you got to bring the axon to resting potential first. Okay? And so since I had these concentrated nodes around VA, I only need to pump out a little bit of sodium and potassium to have this area of the axon to reach resting potential. Okay? Those are the two reasons. Now, there are things called demyelinated diseases. And all that is when something goes on in your body and you start to lose your myelin, right? And so the most common one that people know the most about is something called multiple sclerosis. And this is when your immune system actually attacks the myelin. And then you start to lose your myelin that way. And so here, what you folks are seeing in this diagram is if you lose that myelin, you're going to start to leak all your ions. And remember, you need those ions in order to propagate a signal. So if they leak, you have a hard time getting a signal to travel all the way down long axons. And I keep saying long axons is because in the central nervous system, they're short axons and they don't need myelin is because it doesn't matter if there's myelin in there or not, because the distances are so short that even if you did lose some ions, you still can get the signal across very, very fast. But once you have a long axon, and I mean from the central nervous system to your spleen, or the central nervous system to the skeletal muscle in your pinky, that's a long way, people. And once you start getting an action potential traveling down an axon that long, if you start to lose your ions, the signal is really not going to reach your pinky finger muscles. And if it does, it's a weak signal at best. And that's why common symptoms of any demyelinating disease is you can lose your vision. And you lose your vision is because there's different muscles, right, that are allowing you now to control how much light comes in your eye, where to move your eye, moving a lens so that you can now have sharpness of vision, all via muscles that are controlled by neurons that have long axons, okay? Muscle weakness, all your skeletal muscle, all innervated by a very, very, very long axon, okay? And so that's why if you lose now myelin, it's really hard for you to have coordination and movement of skeletal muscle. Which brings me to my last topic of this lecturette. And I want to talk about myelin and developmental milestones. Now, I want to introduce this topic by showing you my nephew Jace. And Jace is old now. He's 6. But this is Jace when he first was born. And to me, he was so cute because he looked like a Tibetan monk who got into a fight. He had a hard birth. And you can't see it from this picture, but he had a black eye and a black lip. He looked like he got into a fight. And he was just the cutest 10-pound baby ever. But as he grew older, he had what we call developmental milestones. So when you're first born, babies usually really can't do much, right? They can clench their fists and move a little bit. But one milestone is being able to have this, what we call tummy time, right? You put them on their tummy and they can hold up their head, outstretch their arms and their legs in the Superman or Superwoman position, okay? And so here, yes, there's more, honey. Keep watching. And speaking of milestones, that's my daughter. Now, the next milestone then is going to be standing. So this is my brother and my uncle. But Jace at this time was 1. And everybody was worried because he wouldn't walk and he could barely crawl. And everybody was like, oh my God, what's going on? And, but you see here, my brother, he's trying to get my nephew to walk or stand, and my nephew's not having it. But eventually, right, Jace could walk, he could hold his goldfish, yes, and he has this coordinated movement. Now, when you are a newborn, your brain is tiny, and it will grow about 80% to 2 years old, right? And what's going on now, as we now develop these developmental milestones, is myelin. Okay? If you want to have coordinated movement, you need myelin. When babies are first born, they don't have a lot of myelin covering those long axons. But as myelin grows, that's when you hit a developmental milestone. Jace can do the Superboy is because he has enough myelin to engage the skeletal muscles appropriate for this motion. Why was Jace not standing yet or walking here? Because he didn't have enough myelin, right? And also, they have to want to, okay? Because that's another thing. That's behavioral in their mind. But I'm not talking about that. I'm just talking about the physiology. But if you don't have enough myelin going to your skeletal muscle in your arms and legs, you can't stand, okay? You won't be able to do coordinated movements like walking, okay? So developmental milestones are dictated by the growth of myelin covering those long axons. All right, team, that is it for this lecturette. Come back. Bye.